Thank you. Yeah, so this is joint work by Miroslav, Olšák, and Herman Geuvers. And this is a slightly non-conventional talk maybe because it's quite pure lambda calculus that we're going to talk about today. So let me start immediately with a motivating example. So here is a lambda term with two highlighted subterms, and my question is, are these equivalent for some unknown notion of equivalence? Some people might have some opinions on this. My opinion is yes, and the reason I think yes is because I can kind of transform this term by taking by kind of combining the two subterms and putting them in a let, abstracting them in a let. And the claim is then, if I unroll this let, I get exactly the same term, maybe modulo some renaming of variables. So that's why I say that they are equivalent. Some may disagree, but that's my opinion. And then the immediate, there are some questions like so is this the right equivalence that you might have between subterms? Is there something else? So that's something that we'll discuss. And how can we sufficiently find all of the subterms in a bigger term? All of the equivalent subterms in a bigger term, I should say. And before we go on, you might be interested in why would we want this? So our application for why we started working on this was because we wanted to convert a universe of proofs encoded in a Coq proof assistant as a graph. And we wanted to do that such that all of the subterms would be maximally deduplicated. So we needed an algorithm to find these subterms. And then we were going to use this graph, and we have used this graph to do some machine learning on the graph, and machine with the goal of finding new proofs in the Coq proof assistant. So this might look something like this, like you have like a bunch of Coq code with some proofs. It's not very interesting because it needs to be small. And you turn this textual format into a graph. And then you say, like, I want to deduplicate this graph. And if you do this on a really, really large scale with a whole bunch of proofs in hundreds of packages, then you get something that looks like this. So this is the universe of mathematics as encoded into Coq. And this contains hundreds of millions of nodes. And this is what we do machine learning on. And this is fully deduplicated, very dense graph, because there are no two equal subterms in this graph. And everything is connected to everything. And that's a very nice property of graphs. So that's why we want to do this. We wrote some other papers on the actual application of this. So if you were interested in this, go read those papers. There's a website for this. And you can even explore this graph on your own interactively. So if you want to check that out, go look at the websites. There are also other applications, I think, to this work. So you can just think about common sub-expression elimination in compilers. It's like a very standard thing, like you want to find common sub-expressions so that you can get rid of them. You can think about sharing for efficient normalization in like reasonable cost models that compare like lambda calculus to Turing machines, and then you want a beta reduction to correspond approximately to a single step. So that's relevant here. And there's a very good paper that's called Sharing Equality is Linear that you should really read if you find this talk interesting. And then you can also think about if you want to look at what is the difference between two programs. And if you want to have the difference between two programs modulo equal subterms, for example, you're not interested in the names of variables or something like this, then you need to know the hashes of your subterms modulo Alpha-Equivalence, and then you can do structural diffing modulo Alpha-Equivalence. So those are some applications. I'm sure there are more. If you know of more, I would be interested. But back to the actual subject. So the first thing you might think, like, okay, subterms equal, we're just going to use Alpha-Equivalence, right? And if we're going to use Alpha-Equivalence, then we might as well encode our terms using the Brown indices. Because the Brown indices, they're numbers, and we kind of get rid of the variable names in our binders, and therefore we have less equivalence, so to speak. But if you do this, it doesn't work, because this 2 points to a lambda because it skips 2 other lambdas. But this one here points to the same lambda, but it skips only 1 binder. So these 2 objects are the same, but they have different encodings, and as a result, these 2 subterms are not equal encoded as the Brown indices. And that's not what we want. It's problematic. And this is really surprising to me because I thought like, okay, we can just use the Brown indices and then we're done. But that's not true. And it gets even worse, because if I slightly modify this term and I change a 2 into a 1, now this 2 points to a different lambda, but this 1 points to a different lambda, sorry, but the other one points to the original lambda, and now these 2 subterms are equal, but they shouldn't be equal. So these Brown indices, they're horrible. They don't work. Like, don't use the Brown indices for this, except that we'll do it anyway later. But okay, so know the Brown indices, also know the Brown levels, also know code the Brown indices. None of those work. You'll have to take my word for that. So then the question is, well, why don't we use like actual lambda conversion? Because like in this example, these terms are actually alpha equivalent. Like we can rename them, and they do become alpha equivalent. So that works. That's nice. However, not really, because I can kind of narrow the scope of my 2 subterms to exclude a lambda, and now suddenly they're not alpha equivalent. But the bigger term was alpha equivalent, but my smaller term not. That is strange. I mean, it's very normal for alpha equivalence, but if I am wanting to know which subterms are equal, then I want to have this subterm property, right? Where if I make it smaller, then it still holds. So that's strange. And furthermore, I can do this thing where if I rename the G in my term to an F, the term stays the same, right? Because I've just done alpha conversion on it. And now these 2 subterms are equal. So it also depends on which variable names I've used. So all of this is a bit confusing. And a couple of years ago at PLDI, these people made it work. So they did hashing modulo alpha conversion. And there's a paper you should definitely read. But we want hashing modulo context sensitive alpha equivalence. So we want to take into account where, in what kind of context our terms occur, so that we don't get these strange properties about if I narrow a term, suddenly they're not equal anymore while they were before. So we do this through a notion of fork equivalence. And this fork equivalence goes back to this original example where we said, well, if you want to show that these 2 terms are equal, then we just introduce a let. And we merge the 2 subterms into a let, and then we're done. So how does that work exactly? Well, we say this term consists of a context with 2 holes in them and 2 subjects. And that if you want to establish a let between them, then you need to split the context into a base and a fork. And we call the fork a fork because it splits the term into 2 holes. And if you do this correctly, and you can show that the subjects are alpha equivalent and they're closed under the base, then a fork exists. So what that means, closed under the base, is they're not allowed to, the subjects are not allowed to point to anything in the fork. So if there is a lambda in the fork, there is a lambda z in the fork, then none of the subterms are allowed to point to that. They have to skip over it to the base. And if that is true, then we say that there exists a single fork between them, and we write that by duplicating the terms and highlighting on each side of the equivalence a different subterm. But that's not enough, because we have to do this thing where we do the narrowing. So what we say is, if you have established a single fork, then you can narrow the fork to include smaller subterms. And furthermore, you can also have transitivity in your thing. So here is a slightly different example with a larger term and This term seems very scary, but it contains lots of duplicates. So here we say, let's highlight two terms, and we can say that there is a let that there is a single fork between them, because I can establish this let. You have to take my word for it, or if you can look at it very quickly, then you might see it anyway. And then I can narrow these to a very small subterm, and then I can establish another single fork between two of the other narrowed subterms, establishing through transitivity the equivalence between one x applied to t applied to x, and another one. And intuitively, you can think about this as two let introductions. So I can kind of rewrite those terms that you see there with two lets, and each transitive step corresponds to one let. So there's also this picture where you see like there are this is the graphical representation, and there are multiple connections that you make through transitivity. Right. So this is our definition of the equivalence between subterms. And you might now think, well, this is not a very nice definition, and why have you done it like this? Couldn't you do it another way? How do I know that this is the way? And the reason I think it's the way is because it turns out to be equivalent to bisimulation. So if you encode a term as a graph where variables have a back edge to their binder, and then you take these graphs modulo bisimulation, then this turns out to be completely equal to our notion of fork equivalence. And then you can do these cool things where you can say, like, okay, I have one graph, and now I'm going to deduplicate it into another graph where the two terms that we've shown to be equal is now just one thing. So that you can only do this as a graph and not really as a tree. So here's the notion of bisimulation. If you want to read it, I'm not going to go through it. I'm going to assume that you know what bisimulation is. And we say fork equivalence is equal to bisimulation is equal to our algorithm that hashes terms modulo context-sensitive alpha-equivalence. And by the way, this whole notion we call context-sensitive alpha-equivalence. So it's equal to either fork equivalence or bisimulation, whatever you want. So how does this algorithm work? So our algorithm is based on the notion of globalization. So we want to replace variables with the Brown indices with global variables, because we know that the Brown indices are problematic. So we're going to replace them with something that attaches a label to the variables, and that label encodes exactly the right amount of information in order to syntactically compare them in such a way that if you compare them syntactically, they must be context-sensitively alpha-equivalent. And here's the grammar of the lambda calculus that we're using. So it's normal lambda calculus with Brown indices, except that we have this g of t. So a global variable has a label that is itself a lambda term. And this works pretty standardly, just like any other lambda calculus, except that if you do a substitution of a term u into a global variable, then it does nothing. So global variables are not substituted. That's the rule. So then this is our algorithm, our naive algorithm, our silly algorithm. So this algorithm globalizes a term, and it globalizes a closed term. So you have to give it a closed term, and as output it will give a closed term. So the invariant is that it's always closed. And the way it works is, if you encounter a lambda, then you kind of substitute all of the variables that point to that lambda with the term, with a global variable that captures the entire term, and you substitute that in. And if you encounter an application, then you just recurse, and if you encounter a global variable, then you're done. And note that this algorithm doesn't have a case for Brown indices, because it takes a closed term as input. So you cannot get any Brown indices because they're by definition open, and it also, because we're doing this substitution, in the recursion it remains closed. So a little example. This is a very small, very silly example because this is going to get quite big quite fast. So the first step is that we encounter a lambda. So we're going to do a substitution. So this Brown index 0 that you see is going to be substituted with a global variable that has the term itself embedded into it. And then we do the same thing again because we are again at a lambda. So now we're going to do the Brown index 1 that you see, and we're going to again embed the entire term into it. And now we're kind of at the boring stage where we're just globalizing two global variables, and that does nothing, so we're kind of just done now. So that's how globalization works. And now the claim is, the theorem is, that after globalization, any two subterms that are alpha equivalent, context sensitively alpha equivalent, are now syntactically equal. And you might ask why? Well, the reason, intuitively the reason is because whenever we do a substitution, we're substituting a closed term. And the rule with the Brown indices is that as long as the terms are closed, you can syntactically already compare them. And now, any subterm in our globalized term is now closed, which means that any subterm can now be syntactically compared with the Brown indices that are in there. So that's the intuitive. The actual proofs are a little bit more complicated. So now the cliffhanger. So if you want to know more, you're going to have to read the paper, because the algorithm that I showed is not efficient. So this naive algorithm runs in O of n in quadratic time. And that's because it's doing a lot of substitutions. So it might need to do like n substitutions, which are all linear, and that's a problem. So we need to kind of save up these substitutions and do less of them. And the hint to doing that is to say, well, we're only going to do a substitution when the term actually contains two subterms that are of equal size. And only when they're of equal size, then we're going to do a substitution. And why that works, you'll have to read the paper. And if you do that, then you get an O of n, an n log n algorithm. So all the things that are in the paper is formal definitions, much more formal than I did in the talk, proofs, how to implement this practically in OCaml with hashing and all kinds of practical considerations. You can read about that. And an experimental evaluation of how fast is this. Hint, it is reasonably fast, just as fast as anything else that you might compare to. So if you want to know more about this work or the applications that we have for this work, you can go to this website. And are there any questions?
Thanks, Lasse. We have time for maybe one or two questions.
Thanks for the talk. So you mentioned term graphs, and I maybe missed something when you sort of are going past that. Term graphs where the variables are represented by pointing just directly at the binder. Can I think of the globalization algorithm as sort of building the term graph? Because you're sort of replacing the variables with this big thing that just represents the binder. Is that kind of what's going on?
Well, in a sense, it's kind of the opposite of what you're saying, in that you have the back edges, and it's kind of destroying the back edges by copying the term and putting it below it whenever there is a back edge. So it's kind of like the opposite of creating it. It's kind of destroying it in a sense.
Okay. And then, sorry, I have a quick follow-up question. So if I have my term already in this representation where they are referring directly to their I take it in your approach the input is terms within de Bruijn, like with de Bruijn.
Yes.
But if I have my input as the term graph where they're pointing directly into the binders, does that make things any easier to kind of skip a step, or do I sort of have to do the same stuff?
No, it's pretty like in our actual implementation, in our application, is actually as a term graph.
Got it.
And we implement it on the level of term graphs.
Okay.
But honestly, it's probably easier to do it with the Brown indices. But I mean, it's pretty much the same thing. Like the Brown indices are just a tree representation of the back edges. So there's not that much difference between the Brownian niches and term graphs.
Okay.
The difference is minor.
Sounds good. Thanks.
Just a quick question.
Thank you for the talk. It was great. If fork equivalence is the same as bisimulation, I'm curious, what do you get out of the fork equivalence that you don't already get with the bisimulation?
That's a good question. So what you get out of it is that they're very differently formulated.
Yeah.
And one of them is formulated using transitivity and the other is not. And you need this in order to prove things. So you kind of prove that they're equal, and then you prove that the hashing algorithm is equal to either one of them, and you can basically choose which one you do. So sometimes you want a transitivity property and sometimes not, and that makes everything much easier. And I also think it's just a very good insight. And that you say like, okay, these let abstractions, they are kind of just bisimulation with a little bit added to it. And I think that's just insight. Yeah.
Very cool. Thanks.
Awesome. Let's thank Lasse again. And it's